Ever wondered what the difference between TCP and UDP is? Well, you're in the right place. Today, we're diving into the world of network communication protocols, specifically TCP and UDP. These two protocols are fundamental to how data is sent and received across the internet. They may seem like complex concepts, but don't worry. We'll break it down into bite-sized pieces. By the end of this video, you'll have a clearer understanding of these two protocols and their uses. First, let's tackle TCP, otherwise known as Transmission Control Protocol. Think of TCP as the backbone of the internet, the robust and reliable courier that gets our data from point A to point B. It's the protocol that makes sure our emails, web pages, and files reach their destination intact and in order. So, how does TCP manage to be so reliable? The answer lies in its three key characteristics: reliability, ordered data, and error checking. Let's start with reliability. TCP uses a system of acknowledgements to confirm the receipt of data packets. When a packet is received, the recipient sends back an acknowledgement. If the sender doesn't get this acknowledgement within a certain time, it assumes the packet was lost or damaged and resends it. This makes TCP like a persistent delivery person who won't rest until they know your package is in safe hands. Next is the ordering of data. The internet is a busy place, and data packets often take different routes to their destination. This can result in them arriving out of order. But don't worry, TCP has this covered too. Each packet is numbered, so even if they arrive out of sequence, they can be reordered correctly. It's like receiving a book one page at a time, but still being able to put it together in the correct order. Lastly, TCP has built-in error checking. Each packet includes a checksum, a kind of mathematical fingerprint. If a packet arrives with a checksum that doesn't match, it's a sign that something went wrong during transmission. The packet is discarded and a request is sent for a new one. This ensures that no corrupted data slips through the net. TCP is ideal for applications where accuracy and reliability are key. That's why it's used for things like web browsing, email, and file transfers. Sure, it may not be the fastest protocol on the block, but when it comes to delivering your data safe and sound, TCP is your go-to guy. So in summary, TCP is like a reliable postman who ensures your letters arrive in the right order and condition. Now, onto UDP, or User Datagram Protocol. Just as TCP is the meticulous librarian, UDP is the swift courier. It's the speed demon of the protocol world, delivering data with blistering pace. But with speed comes a trade-off. Where TCP is all about ensuring data is delivered accurately, UDP doesn't provide the same guarantees. It doesn't perform error checking or seek acknowledgements from the receiving end. It simply sends the data out into the digital cosmos, hoping it reaches its destination. It's like sending a letter without a return address. Once it's gone, it's gone. Now, you might be thinking, why would anyone use such an unreliable method? Well, that's the beauty of UDP. It's not about being unreliable. It's about being efficient in certain situations. Think about watching a live stream or playing an online game. These are scenarios where speed trumps all. In live streaming, for instance, you wouldn't want your video buffering while the system checks for errors and resends data packets. No, you want a steady stream of data. And if a few packets are lost along the way, that's a small price to pay for uninterrupted viewing. Similarly, in online gaming, every millisecond counts. You don't want lag just because your system is waiting for an acknowledgement packet. You want your movements and actions to be reflected in real time, and UDP allows for just that. In addition to live streaming and gaming, UDP is also employed in voice over IP, VoIP services, domain name system, DNS, lookups, and simple network management protocol, SNMP, among others. In these situations, the speed and efficiency of UDP outweigh the need for perfect data transmission. However, it's worth noting that UDP isn't suited for all applications. For tasks where data integrity is paramount, such as file transfers or email, TCP still holds the crown. So, think of UDP as a fast courier who delivers your package quickly but doesn't stick around to see if it arrived intact. It's about getting the job done swiftly, even if it means cutting a few corners. So, how do TCP and UDP stack up against each other? Well, let's dive right in. To begin, let's consider the Transmission Control Protocol, or TCP. This protocol is all about reliability. It's like a diligent mail carrier who makes sure your letters arrive at their destination, even in a snowstorm. TCP ensures data packets reach their intended destination without errors and in the correct order. It establishes a connection, checks for errors, and retransmits lost packets. This is great for applications that require high reliability, like web browsing, emails, or file transfers. On the other hand, we have the User Datagram Protocol, or UDP. This protocol is the speedster of the two. It's like a sprinter, focusing on delivering data as fast as possible, but doesn't stop to check if everything arrived in order or even arrived at all. UDP doesn't waste time establishing a connection or checking for errors. This makes it perfect for applications where speed is crucial, like online gaming, live broadcasts, or video conferencing. But how do they compare? Well, they both have their strengths and weaknesses. TCP, with its meticulous error checking and retransmission of lost packets, ensures reliability. But this comes at the cost of speed. UDP, on the other hand, is fast and efficient, but it doesn't guarantee delivery or order of packets. So which one should you use? It depends on what you value more, reliability or speed. If you're sending an important document, you'd want to use TCP to ensure it arrives without errors. But if you're streaming a live video, you'd opt for UDP to avoid lag. In the world of networking, there's no one-size-fits-all solution. It's all about choosing the right tool for the job. TCP and UDP, although different, both have their place in ensuring our networks function as they should. Remember, the choice between TCP and UDP depends on what you value more, reliability or speed. So next time you're setting up a network or troubleshooting an issue, keep this in mind. The right protocol could make all the difference. Now that we've tackled TCP and UDP, let's dive into IPv4 addressing. At the heart of network communication lies a crucial component, Internet Protocol version 4, or more commonly known as IPv4 addressing. Think of this as the unique identity assigned to each device on a network. Like a unique house address in a sprawling city, an IPv4 address ensures that data packets reach the right destination without getting lost in the vast digital labyrinth. An IPv4 address is a numeric label composed of 4 sets of numbers, each ranging from 0 to 255. Each set is separated by a dot, forming a distinctive pattern that looks something like this: 192.0.2.167. But here's the kicker. Not all addresses are for public use. Some are reserved for private networks, and some for multicast. This neatly brings us to the concept of subnetting. Subnetting is like breaking down a large city into smaller neighborhoods. It allows us to create multiple smaller networks within a larger network, offering better organization and security. It's like having your own private lane in a bustling city. Remember, every device connected to the internet, whether it's your smartphone, laptop, or even your smart fridge, has an IPv4 address. This is the language that your devices use to communicate in the digital world. IPv4 addressing is like the postal system of the internet, ensuring data gets to its intended destination. Lastly, we'll touch on the need for private IPv4 addressing. You see, the internet is a vast sea of devices, all trying to connect, communicate, and share data. But not all devices need to be accessible to the whole world. That's where private IPv4 addressing comes into play. Imagine a bustling city with countless houses. Now, if every house had a unique address visible to everyone, it would be chaos, wouldn't it? Your postbox would be cluttered with irrelevant mail, and you might even get unwanted visitors. The same principle applies to devices on a network. Private IPv4 addresses are like your very own postbox. They are unique within a local network, but they're not directly reachable from the internet. This means your device can happily communicate within its own network without being exposed to the wider internet. It's like having a private conversation in a crowded room. You're part of the crowd, but your conversation is only for those who are part of it. This is crucial when it comes to network security. By using private IPv4 addresses, we can shield our devices from unwanted external access and potential threats. It's like having a security guard for your postbox who only lets in the mail you want to receive. But it's not just about security. Private IPv4 addressing also helps with efficiency. There's a finite number of IPv4 addresses available, and with the sheer number of devices connecting to the internet, we'd quickly run out if every device had a unique public address. So, by using private addresses within local networks, we're effectively recycling addresses, saving valuable internet real estate. It's like having several houses use the same postbox number, but in different postal zones. So private IPv4 addressing is like having your private postbox secure and efficient. All right, time to wrap things up. We've journeyed through the intricate world of network protocols, distinguishing between TCP and UDP, and understanding when to use each. We dove into the depths of IPv4 addressing, shedding light on its configuration and verification. And we underscored the importance of private IPv4 addressing in maintaining network security and efficiency. And there you have it, a crash course on TCP, UDP, and IPv4 addressing. Stay tuned for more insightful episodes on Tech Spectrum Pro.